our code here is to find square of a given number between 0 to 10, and we are doing that using a lookup table which already has the final result. I think if you know basic multiplication, then to find square of any given number, we know that we have to take it in any register. Let's take an example of a register R0, multiply R0 by itself, and then you get square of that particular number. Okay, that's the easiest way to get the output. But now we want to see how exactly we can get data from lookup table, okay, instead of performing any calculation. Fine. Before we see the code, first of all we should know what exactly do we mean by a lookup table. Okay, a lookup table is a data structure, often an array or a simple table that is used to map input values to output values for fast retrieval. Instead of computing a value each time it is needed, the system can just look it up in the table, which is usually much faster. In short, instead of doing complex calculations, just use a pre-computed result. That's what we are going to do now. The very first thing we see here is area, which is an assembler directive which instructs it to give a segment or give an area in the memory in order to store all these instructions. Okay, then we have a random name here. Code informs that these set of data are instructions. Read only because we don't want any modification to happen to this particular code during runtime. Entry indicates where exactly the code is starting. Okay, then start is a label. This is our actual code. Okay, so the very first instruction that we see here is LDR R0, equal to table 1. Table 1 is our lookup table, okay, wherein you can see all these values. That is, DCD here indicates we are storing 32-bit values, okay, and the very first value we are storing is 0 because square of 0 is 0. Okay, second term which is stored is 1 because square of 1 is 1. Then we have 4, that is square of 2. Next we have 9, which is square of 3. But after that you can see there are some changes. We know that 4 square is actually 16, but here the answer is stored as 10. The reason is when you write DCD 0x and 0, all the zeros and whatever number you're writing here, this is nothing but hexadecimal representation. So hexadecimal representation of 16, which is a decimal value, is 10. Okay, then we have 5 square as 25, which in hexadecimal is 19, 6 square as 36, which in hexadecimal is 24, and so on. Okay, so don't get confused with this particular change of values. It's just that we have represented our required square number in hexadecimal format. Okay, so now when you say LDR R0, equal to table 1, the address of this particular label is now loaded into R0. Okay, then R1 we are storing the actual value whose square we need to find. LSL is nothing but logical shift left. In case of logical shift left, data bits are shifted to left and the vacant locations are filled with zeros. When you perform logical shift right, you are shifting all data bits to right side and vacant positions are filled with 0. Okay. Okay, what this instruction does is any data which is there in R1, in our case it is 3, we want to find square of 3. If you consider 3, it is nothing but decimal or hexadecimal value. Okay, if you write it in binary, it is nothing but 0, 0, 1 1. When you perform logical left shift, you should know that, okay, this entire content is moved to the left side, which is nothing but you will get an answer 0 1 1 0. Okay, this if you perform logical left shift by 1, you're moving that side. What if you perform 2 times? You will get the answer 1 1 0 0. Okay, if you notice that, okay, for any given term, whether it is 2 4 6 8, whatever term, whenever you perform logical shift left by 2, it's always, okay, multiply by 4. Okay, because every logical shift left is nothing but multiply by 2, and every logical shift right is divide by 2. You can try this for any number and you can see that answer. So because we already know this, we should know for any given number, if you perform logical shift left by 2, you will always get multiplied by 4, because every left shift by 1 gives you multiply by 2, and every right shift will give you divide by 2. So here 3 will be shifted 2 times, okay, because here it is written 0x2, 2 times it is shifted to left side. Okay, fine. So what happens then? If you are speaking in terms of decimal, it is 3 into 4, which is nothing but 12. Okay, why exactly we are doing this? You will get to know when you will see the memory organization of this particular data. Okay, so 3 4s are 12. 12 is stored in R1. Okay, and then to the initial address. Now if table 1 is your initial address, okay, to that you are adding whatever is the multiplied content and the total here, because let's assume the initial address as 0, 0 plus 12 is 12. So that address will now be there in R0 and the content of that address is moved to R3. Fine. That is what we are doing. Here no operation is written. It is just used to create some delay. Okay. Okay. The very first thing that is happening is table 1's address is loaded to R0. That is 20. So that I'm pasting in the memory window so that I can see what exactly is stored here. If you notice here, because it is DCD, this is considered as a 32-bit data. Okay, so because it's 32-bit data and each location occupies 8 bits or 1 byte of data, so 8 into 4 is 32. Okay, so that's why we have 1 2 3 4. Okay, 4 locations are used to store the very first data. Then you have the next data here, okay, which is stored in next 4 locations. If you can see here, it is 0 0 0 0 0 0 0 1. Okay, but it is stored in reverse order. That is because we have Little Indian system. Okay, so these 4 locations store the value 1. Then we need to store the value 4, which is stored in these 4 locations. Okay, 9 in these 4 locations, 10 in these 4 locations, and so on. Okay, so don't get confused. Okay, the initial 4 locations are here. This is the square of 0, square of 1, square of 2, square of 3, and so on. Okay, and now I think you can understand why are we doing this particular logical shift left. Okay, so here if you see, logical shift left has 0x2 always multiplies the given data by 4. Okay, that is a fixed thing that will happen. Okay, so let's see what is happening here and why exactly it is required. Let's consider the first case 3. 3 into 4 is nothing but 12. So when you multiply by 4, that answer 12 is nothing but added with initial address. Initial address is this value. Okay, that points at the first location. What will happen if we add by 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the location it will be pointing at, and that is exactly our answer. How is that we are getting this value? The thing is, each data occupies 4 location. Okay, so if you want to find square of 3, multiply it by 4 so that you can reach that particular spot. Okay, now let's consider any other data. Okay, let's consider the value of square of 2. Okay, answer should be 4, but how are we finding that? Initially pointer will be at this particular location. Okay, because this particular instruction make sure we multiply 2 by 4, which is 8. So if it's pointing here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so entire task is done by this particular instruction only. For any given data we are multiplying by 4 because one particular value occupies 4 location. Okay, because we are starting from 0, so any number whose value is to be found, we have to just multiply it by 4 and add it to the initial address. Okay, that is nothing but 20. Let's see how exactly it's happening here. So R1 is 3. We want to find its value. Here, why is it C? It is because when you perform logical left shift twice, okay, on 3, the answer you will get is 12, which is nothing but C. So next what we have here is nothing but the received answer, whatever is there. Let's assume in our case C. That is added with initial address of R0. Okay, so let's see how it happens. That gives you 2C. So okay, so 2C is nothing but this particular location that we are loading here. We are loading content of R0 into R3. Okay, so here what is happening is our content of R0 is nothing but 9, which is loaded into R3. So that is how we are finding square of any given number. Now let me just take any other number, higher value. Okay, let me take a value like 6. Okay, as you can see here, now when you multiply 6 into 4, the actual number is 24. Okay, but in hexadecimal it is 18. Then it is added with initial value, okay, of the address, that is 20. So that will now point at this particular location. Okay, that's all.